Good afternoon and welcome to a replay of our presentation for the American Modelica Conference in 2024. The presentation is titled Modelica as Model Aggregator for Holistic Architecture Validation of Electric Vehicles. And the presentation will be about the integration of model-based systems engineering and Modelica, or systems architecture, and the simulation domain, to enable using simulation models in very early stages of the development phase of complex cyber-physical systems. So let's begin with a word about the need for continuous engineering. Here we see the major steps of a development cycle, including the different engineering disciplines from requirements up until the manufacturing of a product. And in this process, there are many stakeholders, the number increasing with the complexity of the product and the process. And these many stakeholders, they have their own tools, with their own models, and with their own processes. So there's no digital continuity from one domain to another. All of these domains are disconnected, and these silos are harming the collaboration that should be in place. This means that we have very late application of simulation in the process, and this causes higher friction. One major heavy machinery manufacturer says, complex systems require early stage architecture V&V with available digital artifacts to manage variability and versatility. We want to come to a holistic design of these complex systems by integrating different domains and enable the reuse of information from one domain to another. This is an incremental process, and it's what's behind the terms model-based systems engineering. The requirements, functions, logical structure, and the physical implementation of this logical structure, RFLP. This is the left side of the adapted V model, and that's why it has this shape. There's a horizontal and a vertical cascading of these design entities and different representations of the models. The full product line level on top, or the subsystem level. Each of these levels of detail of the system go along this process of description of requirements, functional, logical, physical. There's also a vertical flow of information. For instance, the physical layout of the portfolio level drives the logical description of the product. It allows us to drive requirements on the next level. So there's tight integration between these different entity layers, and this should be enabled by the holistic integration approach. So how can we achieve digital continuity along this process? At ESI and XPI, we use a tool-agnostic approach. There's a layer at the front, which we call the client side, where the authoring tools are creating and consuming content. And we have a layer at the back with data storage that stores content created by the engineering tools. In between that is a middle layer that acts as a translation of information between the front-end tools and the back-end tools. This allows front-end or back-end tools to be replaced with alternatives. But the API that is connecting the front and back end stays the same. There's no change in the integration layer. So from that perspective, we are tool agnostic and easy to adapt with low maintenance costs. This is the approach that ESI has implemented for the integration of development processes for these complex systems. A demonstration of this is shown in the next section. The background for this example is of a commercial electric vehicle, that is, a semi-truck for perishable goods. This is a very high-level description of the stakeholder needs. We want to be able to carry a meaningful payload, and we want to fulfill relevant certifications. In this example, there are two decisions at the architectural level. The first is about the power source, either a battery or a fuel cell, and the second is about the cabin heating. It will either be a heat pump or it will use resistive heating. And of course, there are also several requirements. Some of them are shown here. These are high-level performance requirements, and performance requirements are selected because we want to use system simulation to verify the fulfillment of these requirements by the architecture. And so there are range, consumption, climbing power, comfort, and battery health requirements. So the process which we go through is covering the left part of the V cycle, the design and verification phase. We start from the requirements in a certain tool, and based on these high-level requirements, the system architecture is designed, which is more or less a formal process where the functions of the system are defined and the logical architecture is derived from the functional analysis. And then we reuse this information on the system architecture and also the requirements to automatically build simulation model templates. So we transfer the information from these system models to the simulation domain, and we augment them with simulation and evaluation that represent the scenarios described by these requirements. And then we can use these models to run verification simulations in order to find out if the architecture fulfills the requirements. There are 4 core aspects that we transfer from the holistic system model to the simulation domain. The first one is the architecture itself, the logical structure, that is, the components and their relations. To do this, we use stereotyping, which is a feature in SysML where we extend the information of the structure in the SysML diagrams to include the physical domain behind it, so that we can create physical simulation model templates automatically based on that information. And then we fill these components with behavioral components from the physical model libraries. Or we use functional mockup units, or FMUs, if these models are already existing. The second aspect we transfer is the design parameters from the system model. Many design parameters are already defined at the architectural level. There are parameters that are attached to certain logical components in the system model, and we automatically extract and transfer this information to our system model templates. And these parameters are automatically allocated to the various components. And these parameters then are also available in the test management platform. The third aspect is the topic of configurations. How to represent variants and configurations. We use the information about variability. For example, if a component in the architecture is flexible or variable, then this information is transferred, and we use for the implementation of the variability the replaceable model syntax from Modelica. Also, we extract the information about configurations, which is represented in SysML variability diagrams, a new feature in SysML 2.0 specification, which was recently released. Based on this information in the system model, we extract or create a specific configuration of the system. The last aspect that we reuse from the system model is test model generation. This is also contained in the requirement diagrams, where we have a linkage between the requirements, functions, and logical diagram. This is used in the simulation for a function-based test approach, so that the engineer is just selecting part of the architecture by function, because the teams are usually allocated by function. So the engineer that's doing the simulation model is not overwhelmed by the full architecture, but can select the function that he is allocated to, and only gets the components that are connected to that particular function. The extracted test models are augmented with scenarios to verify the requirements. These are some results from this specific use case. We tested this design using a route that was exported from Route Planner, and we compared 2 different architectures in 2 different conditions, one for summer and one for winter. And based on the results that you can see on the right, we can see that the battery uses less energy. However, we don't consider in this analysis how the electricity is produced. And we also see that the heat pump architectural choice consumes less energy for the cabin heating. It also provides the benefit that we can cool the cabin. Taking this into account, we have a decision for a configuration, a battery, and a heat pump. And now we can do a more detailed design of the system. We go to the next level in system description and decomposition and refine the simulation models with more detail inside these different components in order to run more precise design tasks. As an example, the cabin comfort requirement is evaluated in more detail using a parameter study for a range of different ambient conditions from -40 Celsius to +40 Celsius. And we can see for the different combinations of design parameters whether the comfort requirements are fulfilled. This enables a design space identification for the design parameters. On the right side, we see a parallel coordinates diagram. On the left, we see the inputs. Then we see two design parameters, the trailer cooling power and the cabin HVAC power. And in the last column, we see whether or not the requirement was fulfilled. Then we can feed back this information into our holistic system model. This slide gives us an overview of the overall requirements view within the Validation Campaign Manager. We see that 6 out of the 8 requirements are fulfilled. So now we would have to go back and look at the design parameters that affect the 2 requirements that are not fulfilled, and also check how they affect others. Let's conclude with some takeaways. We've achieved digital continuity by validating and verifying the architectural design at a very early stage when simulation is often not yet taking place at all, even though it really makes sense to use simulation at this early stage, as many expensive decisions are being made. We've created a tool-agnostic approach based on linked data. No duplication of data. Instead, there's a single source of truth. And the user's not bound to an all-in-one monolithic solution. Thank you for your attention, and if you have any questions, we encourage you to reach out to either ESI or XBI. Thanks again.